Welcome to a review session for the final exam in ECE 320 during the spring semester of 2019. You do have some supplemental material for Unit 10, and I know it might look like a lot, but there's really only about 60 minutes of video content, and I've heard that people double time that or step that up a little bit with respect to my speaking. So it won't take you maybe that long if you view that, but the notes are also there. And homework number 10 is due today. Today's reading day, and that's dealing with filters, and we'll try to talk a little bit about filters relative to the final exam. But our final exam is on Wednesday, May 8th, and it's in the it's not in the Chavez room, it's in the Chavez room. I'll try to correct that typo. But it's in the normal classroom, room 111, from 3:30 to 5:30. And additional office hours are here. They're in an email that I sent this morning, and they're posted outside my office. What I want to do now is just go through the following. Here's the information about the final. It's comprehensive. There will be 15 questions, and they will be uniformly distributed throughout the content of the class. They won't be emphasizing material that was after exam number 3, although there will be material on the final that was covered in the class beyond exam number 3. You can have 4 sheets of notes, front and back, 8.5 by 11. If you need Laplace transform tables, make sure those are included in your 4 sheets of notes. And if you want to bring a protractor or a ruler, you may, or a straight edge or a compass. I don't know that we need a compass here, but in another class, a compass can be used. So you can have all of those drawing instruments. Graphing calculator, but no class notes, no textbook, no phone, or no computer. And the material that's on or in the module on D2L concerning the final exam is a list of topics that essentially, I hope, is what we've covered this semester. There's a couple of practice final exams, and there are answers. Well, yes, there are answers to those. Not necessarily solutions, but answers to those, and the notes and video from this final exam review session will be on or inside that module. So what I thought I would do now is actually talk a little bit about, there were some questions submitted on the quiz in D2L concerning the final exam, and let me see if I can pull up some of those relative to, well, who knows if I'm going to be able to find them, but let's see what we have here. Here's one that maybe you might be interested in. And it's somewhat Bode plot, but it sort of has a place in the question that was asked for reviewing on the final, and that was the following: how to identify filtering characteristics given a transfer function. So this is, in fact, you're given some of the filtering characteristics of the filter that you're wanting, and you're trying to now determine which of these cases that falls into. And so now you're saying, oh, I need to design a filter that's a normalized low-pass filter that satisfies the following, and it's obviously not going to be normalized if we now have this second specification, which it says a low-pass filter with a bandwidth of 1,000 radians per second. So now we want a Butterworth characteristic. That means it's maximally flat in the passband, and all of the break frequencies will be at minus 3 dB. from the break frequency, which in this case is 1,000 radians per second. We want a passband gain of 40 dB. And what does that mean? We'll have to figure that out. And a high frequency phase of minus 270 degrees. Now, is there anything in that information that might be related to what's down below? And now I'm asking, what statement is true about the filter order and the frequency scaling? So now we're trying to find out something about the order of the filter and the frequency scaling. So the first one, the Butterworth characteristic, that really doesn't tell us anything about the order. The order can be anything we want with a Butterworth. The second one, we want a low-pass filter with a bandwidth of 1,000 radians per second. That actually tells us something about the frequency scaling. The normalized Butterworth filters that we have available to us have a cutoff frequency of omega sub 1 equal to 1 radian per second, and that, in fact, is really what we are considering to be our omega sub 1. Meaning, if we're asking here, it's asking for a k sub f, so we need to now find a k sub f that realizes this relationship or satisfies this relationship, where omega sub 1 is our initial and omega sub 2 is our final frequency in scaling. We know that the nominal frequency, the normalized, is 1 radian per second. We're told that we actually want a low-pass filter with a bandwidth of 1,000 radians per second. That's now omega sub 2. This is now omega sub 2. And I could give this to you in Fs, in hertz. I could give it, so you need to pay attention. But now our omega sub 1 is in radians per second. Omega sub 2 actually has the same units. And now it's, I think, pretty clear that omega sub 2 equaling 1,000 is k sub f times 1, which this is now our omega sub 1. And we can solve for k sub f by dividing by 1. So now we know that k sub f is 1,000, and now you're looking at, oh, maybe A or C are possibilities. Now you're saying, okay, how do I determine filter order? 3 says a passband gain of 40 dB. What does that mean? Does that give us any information about the order of the filter? Yes, so now we're actually saying something like the following. We're saying, oh, these specifications are saying that this particular point is 1,000, and this value in the passband is plus 40 dB. Or if we converted that into an absolute number, we're saying that 20 log of k is equal to 40 dB. And we could find k on our transfer function, or the gain, the constant, by dividing both sides by 20. This is log base 10. So now we have log base 10 of k is equal to 2. And I think you can see what k needs to be here. If you take the anti-log of both sides, k is in fact 100 in terms of that's the actual gain that you want your filter to be producing. But that doesn't depend on the filter order. That's a red herring. That's just additional information in this problem that you don't need to determine the filter order. What else were we given? And what you may have seen in that is you may have locked into 40, and we do have the possibility of going up or down by 40 dB per decade in magnitude slope. So if we were going down minus 20 dB per decade in the stop band, that would indicate a second order filter. But I didn't say minus 20 dB per decade. I said the passband gain is 40. What you are given here is a high frequency phase of minus 270 degrees, which means in the high frequency region, and what's considered high frequency in this particular case? It really doesn't matter in this problem, but what would be considered high frequency in this case, in this problem statement? Something bigger than 1,000 radians per second, and if we want our phase to actually be finished contributing or to be leveled out after it's been sloping or changing, we want to be a decade beyond the last break frequency. Our break frequency is 1,000, so high frequency here would be 10,000. And if we needed to plot this, so here is 1,000, and here's 10,000. Now we're saying that the high frequency phase is minus 270 degrees. If this is now our phase plot of this filter. And does that tell us anything about the filter order? What level of degree tells us about a single pole factor? Or what's the angle contribution from a single pole factor? If I now had something that looked like 1 over s plus 1, where is that going to go phase-wise at high frequencies? Where will that end up? Or you could say, well, I don't know. Let me draw the S-plane plot. And you say, now I'm at minus 1, and I have a pole there. As you go up and up higher, what's that angle approaching? As you go higher up in j omega. 90 degrees. And since it's downstairs, it's going to be subtracted. So this one would give you minus 90 degrees, each pole factor, each linear factor. And now the problem says that you have, when you get to all of your poles being active and contributing all of their phase, you're going to see minus 270 degrees contributed. Does that tell you anything about how many poles you actually have? Yes. So now you have 3 poles, and that's all we have in a low-pass filter. That's our filter order, and so now you know that it's answer C. That this minus 270 is actually saying we have a third order system. And in that case, you could now say, oh, I've deduced that this must be C is my answer for this particular problem. So the question on D2L was actually concerned more with this problem, I believe. This question is how do you tell from a transfer function what your filtering characteristics might be when you're just given a transfer function? And what do you want to do in this case? You're really just saying, what's the magnitude look like for the frequency response of this? And that you can, I hope, quickly start saying something like, oh, let me write this in time constant form. And you have that. And what's the magnitude of this look like if you wanted to consider all of the different pieces and parts? Well, if you just start looking at all of the different pieces that are contributing, let's say here's 10 to the minus 1, 10 to the 0 or 1, here's 10, here's 100, and that's really all we need for magnitude information. Do we have a constant factor in this transfer function expression? Yeah, we have a 10. So if we looked at that in dB, we would say 20 log of 10 is going to be given to us by the constant. So now we say 20 log of 10, this is coming from the constant, is equal to 20 dB. And now we know the contribution due to the constant can be accounted for by that flat line at 20 dB for all frequencies. We also have a pole at the origin, and what does that look like in terms of its magnitude, shape, or properties? What does a pole at the origin do? Does it break? Does it have a particular break frequency? Is there some place that, or for low frequencies, is it 0 dB, and then at high frequency, at somewhere but from low frequencies to high frequencies, it actually transitions and breaks? No, it's always on, isn't it? This pole, and it's downstairs, it's always on. That means there's just one pole at the origin, and it slopes now at minus 20 dB per decade. And where do we pin it? We pin it where it would have a value of a magnitude of 1. So we take 20 log of 1, it's going to be going through 0 dB at omega equal to 1. So now we could say that the, whoops, it's not what I wanted. I want to now be going through 0 dB. Here is 0 dB. And I'm always sloping, which means that a decade before that I would be at plus 20 dB. A decade after that I'm at minus 20 dB. So that pole at the origin is giving me something like that. What else do I have happening? Well, I've already accounted for this pole at the origin, so that's what the green was. This is the pole at the origin. I've accounted for that, and now I have two more factors to introduce or put down on the paper to account for them in this Bode plot. I have one zero factor that has a break frequency of 1. That means that it will... Do you want me to do it in another color than what I've done? I've done blue and green. Do you want me to do another color? Okay. You're not very demanding, are you? So let's see what color I can find. How about that bright color? And that will be our 0. How do I draw this one? Does it break? At low frequencies, is it really going to be 0 dB? That factor? The factor I'm talking about now is S over 1 plus 1. At low frequencies, what does it look like? If we put in j omega for S and we let omega be tiny, now we have 1 plus j tiny. So we can neglect the j tiny and we just have a 1. We say 20 log of 1, that's 0 dB. So yes, it's going to be 0 dB until it breaks. And where does that one break? If we write it in this way, it's breaking at that frequency that's underneath the S, which in this case is 1. We're 0 dB until we hit the break frequency, and then what do we do? Where is it? Is it upstairs or downstairs? It's a 0 factor, it's upstairs, so we're going up. And we're sloping up at 20 dB per decade after the break, which means that we would be flat here. I don't know that I even want to draw it, but I will. And then it starts going up at 20 dB per decade after that break. And I only have one more factor to consider, so I've now just drawn that one. And I'm guessing you want another color for this. I'm not very effective with selecting colors. Let me do brown here and see what happens. Do you see that this is going to have the same shape? It's just going to break at a higher omega. It's now breaking at 10. So now we would go up 20 dB after 10. And this is now our 0 at omega equal 10. Oh, now I have to find that color again. Did I use that one? This one was due to the 0 at omega equal 1. Do I have everything labeled? And you could just look at the different colors. I have a constant, which was blue. I have a pole at the origin, which was green. I have a 0 at 1, which was magenta. And I have a 0 at 10, which was brown. And now I need to combine those to see what's my overall shape, or what's the filtering characteristic associated with this transfer function. How do we do that? We need to combine all of these dashed lines. And how do we do that? Well, we have this green line that's always on. So we're not starting flat in this case. We're actually starting sloping down, but we could adjust, well, and to do the official magnitude plot, we need to adjust every point in our magnitude plot up by 20 dB. Should I do that after I've combined all the others or now? It doesn't matter. But I could combine all of these sloping ones and then at the end shift everything up by 20 dB. And this particular filtering characteristic doesn't really depend on the absolute shift in the magnitude. But suppose that I do want to just add in the gain constant from the beginning, just so that you're not completely confused if I did it some other. So now what I would do if I'm sketching this, I would walk to the low frequency end of my plot and I would say, okay, how far to the left, how low in frequency do I need to go in order to have nothing be breaking yet? I'm obviously having a slope from this pole, so I could go all the way to Phoenix. I think that's low frequency in terms of direction in this classroom, trying to get oriented. But I could go all the way to Phoenix and still be sloping with that green. But nothing else kicks in until 1. So really I could just go back to point 1 and I'm far enough or low enough in frequency in this particular plot. But let me just go back one more decade just to be safe and say, let's now go back to 10 to the minus 2 or 0.01 and say, let me start drawing my complete magnitude response from that frequency on. And what do? I go to that frequency and I say, what is actually contributing magnitude? Well, I have 20 dB, and I actually have how much from my pole at the origin. I'm back 2 decades from when it was 0, and it's sloping at 20 dB per decade. It's contributing 40 at that point. I add in 20, so I need to be in my total at 60 dB. That should be 20 dB above where I was with just the pole and no constant introduced. Or my total magnitude looks like that. And I keep going with that. Where am I going to be at when I hit 1? What's going to be my magnitude when I hit 1 in frequency? What will my overall magnitude be? My pole is at 0 and nothing else has kicked in yet except the constant, and it was giving me 20 at all frequencies. I should be at 20 dB at omega equal to 1. I can now just keep going down here until I hit 20 dB. And now what do I do with my red line, which this is now the total magnitude plot? What happens now? Well, now you just start looking at the slopes. You have green going down at minus 20 dB, and you have magenta going up at plus 20 dB. Those cancel. So your net is 0 dB per decade. You're flat until you come to another frequency that introduces a new change or another slope, and that slope change now has been introduced at omega equal to 10, and at omega equal to 10 you start going up 20 dB per decade because you've reached another 0 factor. And now that's the last thing that is there, and now you just keep going up. So you now have this red shape for your magnitude, and that's supposed to give you your frequency response characteristics or your frequency behavior for this particular transfer function. And what would you answer based on this shape of the red magnitude curve? This is a band reject, isn't it? It's not favoring a certain band, it's rejecting a particular band. So now you could say, oh, that's C, and I'm going to now say that's a band reject. And you could do this for different kinds of transfer functions. If somebody gave you h of s that might look like, oh, let's say it's now 20, no, let me not even do that. Let's say it's s plus 1, and let's say this is s plus 10, s plus 100. What's that look like? So this is now a different, but now I could say, how did I say, what filtering characteristic does this transfer function possess? Do you see that you wouldn't even have to go through all of this Bodie-Plot stuff that we just went through, really? You just have to look at the breaks and say, oh, what happens at low frequencies? At low frequencies, you could say, okay, S is going small. Let's let S be 0, and we're going to be at 1 over 10 times 100, or 1 over 1,000. We're going to be at some constant value. We're not always sloping either up or down because we have no polar 0 at the origin. We're going to be flat at low frequencies in terms of magnitude. And then what happens? So now we're doing this rather quickly. We're saying, oh, we're flat until when? Until 1. So we just look at these different breaks and we say, oh, here's our first one. And at 1, what are we doing? This will be 10 to the 0. That's 1. What's happening now relative to this transfer function's frequency response? We're looking at the magnitude of h in dB. What happens when we hit a 0's break frequency? What happens beyond that? Now we go up, don't we? 20 dB per decade. So now we would go up until we hit our next break, and in this case that next break is a pole. So now it contributes minus 20 dB per decade. We were going up 20. We now say, well, let's introduce a minus 20. That means we're flat. So at 10, we now go flat until we reach our next break frequency, and that's this pole at 100. So now at 100, it's a pole, it's downstairs, it contributes minus 20 dB per decade, and it looks like that, and that's the last thing to kick in. And now what would you say this filtering characteristic is? So this one could go kind of either way. It's favoring a particular band, but it's also low pass in behavior. So I might have to kind of give you credit for either of those responses. It's favoring a particular band, but a band pass usually does something like this, doesn't it? It's attenuating at low and attenuating at high. This one doesn't really do that. It's okay with the low. It accents some frequencies between 10 and 100, but then it starts rolling off. Now I could ask you, and so I might prefer to say this is a low pass filter characteristic, but it has kind of a weird low pass behavior because it's actually enhancing the frequencies between 1 and 100, or actually even beyond that. Between 1 and 1,000, it's accenting those particular frequencies. If I now ask you, in this particular case, what's the phase at high frequencies, what would you say? You could say, well, after everything kicks in, how many net poles or zeros do I have when I go, and what is considered a high frequency in this particular transfer function based on our argument? A decade beyond the last break, our last break is 100, so we would say high in this particular transfer is 1,000 radians per second. What's low frequency? a decade before the first break, and in this case it's 0.1 times 1, or 0.1. So low frequencies would be below 0.1, high frequencies would be above 1,000, and what's my phase at high frequencies? How much phase is the zero factor going to contribute? 90. So now I'm at 90. Then I have a pole at 10. What does it eventually contribute? Minus 90. Now at that point I'm nothing in terms of angle. I'm 0. And then what happens to the pole factor at 100? How much does it contribute? Another minus 90. So you look, you have 2 poles, 1 0. Your pole 0 excess is actually 1. So at high frequencies, a net look like 1 pole. So your phase at high frequency would be minus 90 degrees. Your phase at low frequency, and here high frequency we said was greater than 1,000. Phase at low frequencies is 0 degrees, and we said low frequencies was when omega was less than 0.1. Questions on that? Yes. So now what is your magnitude at low frequencies? So in this case, do you have a DC gain? Do you have a DC gain? Is H of S bounded when S is equal to 0? Yes. So DC is pretty low. That's low frequency. You could say, okay, my low frequency gain, I'm going to find the DC gain. It should be the same as your low frequency. In this case, your DC gain is 1 over the product of 10 times 100. So this now says H of 0 in absolute terms is 1 over 10 times 100. And you could do that if you put it in time constant form. You would factor out a 10, you would factor out 100, and you would see you have 1,000 sitting downstairs. Or you're now, if you wanted to say the DC gain, in absolute terms, that was H of 0. (10 to the minus 3). In dB, what is that? It's not very big, is it? Actually, it's a large negative value. This is now 20 times the log of 10, but now we can pull that exponent out front. Log of 10 is 1. So we're starting pretty low in this one. We're starting at minus 60 dB at low frequencies. That would be our gain at low frequency in this particular problem in dB. In absolute terms, that's 0.001 or 10 to the minus 3. Yes? Yes, so if you're just trying, the question was if you're just interested in the shape, you don't really need to know where we're starting, what level we are at. In this case, that's minus 60 dB. If you had to sketch the whole thing, yes, you would need to know where am I starting, minus 60 dB. But in this case, I might be just asking, what's the frequency characteristic of this particular transfer function? And now you're saying, okay, well, it's low pass. It favors a particular frequency interval between 1 and 1,000. What if you had something like this? Suppose a system's input, x, is given by a sum of 3 cosine terms. That's really just a Fourier series expansion of some periodic waveform. We didn't get there, but you have the tools to answer this question without knowing this is kind of a Fourier series problem. You'll do this in 340A, create Fourier series and Fourier transforms. But you can, now we're saying, okay, if the linear system has the following ideal transfer function, that's what this is down here. This is basically a frequency response. It's not so much a Bode plot because the magnitude is not plotted in dB, it's plotted in absolute value. It's just the actual gain of h at various frequencies, and here's your phase at minus 45. Only for certain frequencies. And those are in omega. So what does this chart give you? It gives you your magnitude and angle of any sinusoid that might be applied to this system between 4 radians per second and 10. And any frequency between 4 and 10 will be amplified or changed in magnitude by 4. And what's its phase? It's minus 45. This is how you could actually pull off this same kind of information if I gave you a Bode plot. You would say, oh, what's the magnitude at a particular frequency and what's its angle? What do we do here? Suppose a system's input is given by these 3 terms. And now we want to know what are we going to see at the output. And this is ideal because now we're saying that between 0 and 4 we have 0 output because h is now 0. If you put in a sinusoid that has any frequency between 0 and 4 radians per second, it won't be seen at the output of this system. This is ideal. And any frequency beyond 10 won't be seen because it's also at 0. So I'm really trying to see if you understand, 1, how to determine sinusoidal steady state behavior, and can you start to explain or utilize some of this frequency response information that you're provided. What did I try to then get you keying in on here is, oh, do we have any frequencies between 4 and 10 radians per second in this x of t? If these frequencies were 0 to 4 or 10 and above, we would have 0 for our output. So I do have a none of the above, huh? A Dr. Marcelin special. What am I asking? I'm initially saying, what are these frequencies? We have cosine of omega t, where omega 1, omega 2, and omega sub 3 are in different arguments of this x of t overall. What's this omega 1? It's 2 pi, isn't it? 6.28. So this is now 2 pi, which is 6.28. Oh, that's between our 4 and 10, isn't it? What about this frequency? Let's call this one omega sub 2. That's now 4 pi. Well, that's twice omega 1, isn't it? So that's now more than 12. So this is now, let's say, 12. We don't need to be any finer than that. And what's this one? 6 pi. Let's say that's 18. Let's do some rough rounding. Because what do we know these last two terms in x of t are going to produce at the output of a system that has this characteristic? 12 is right here, and 18 is clear over here. We aren't even going to see anything coming out of the system at those frequencies. The only term that we really need to focus on is that one that will be in our sinusoidal steady state output. And now this system is linear, so I said it's a linear system. If we're shaking it at 2 pi radians per second, what are we going to see coming out? 2 pi radians per second. So now we look at down here and we say, okay, do any of these have a 2 pi? And we say, oh, A and C look to be possibilities. C, wait a minute, we don't have 4 pi coming through. That one was attenuated. And 6 pi is attenuated because of the magnitude being 0 at those frequencies. So we've already figured out probably unless it's none of the above. But if we now inject a cosine at 2 pi into a linear system, we know y is going to be shaking at 2 pi. But we also know that system might influence the amplitude and the angle or the phase. And this information, these two plots, tell us how that magnitude and angle are introduced from this system. What's the amplification going through this system at 2 pi? It's going to be upped by 4, by a factor of 4. And what's its angle? Minus 45. So do you see that in steady state, we started with a magnitude of 1, so we increase it by 4. And hopefully that's one of our answers. 4 cosine of 2 pi t minus 45 degrees. We just go with A. Another question that was asked was the following, if I can find it. It was a convolution question, I think. How do we know what's going to happen in this particular case at a certain value of y or a certain interval of y? If y of t is the convolution of x and h, where x and h are given as explained here, find y for t between 4 and 5. What? That's okay. You can flip and slide one of these. Which of these would you probably prefer to flip and slide? probably the one that's not as involved. I would say flip and slide H. And you could also say, well, let's just ask some additional questions beyond this, since this is a review session and who knows what will be on the final. When does Y start? When do you start seeing a non-zero output? So forget X for a minute. H, let's say, is our ideal impulse response. That means that if we hit this system with an impulse at 0, what are we going to see at the output? We will see nothing until 2 units of time later. And then we'll see -1 for 2 units of time until 4, and then we won't see anything thereafter. So if we hit this system with an impulse at 0, we wouldn't see anything happen, and then 2 units later we would see it -1, -1, -1 until 4. Well, what are we doing with X? We don't even hit this system until 1, and once we hit it, when do we see something? 2 units later. So when would you expect to see something at the output non-zero? 2 units beyond 1, so 3. So you would expect to see a non-zero Y starting at 3. Is that clear? And that is as trivial as saying, well, I can actually just add 1 and 2, and that gives me 3. When will we finally be done seeing this system moving? We stop applying an input at 5, and we have to wait 4 units of time beyond when we stop exciting it. So we will stop seeing any action at 9. What did we just say? Y of t is non-zero between 3 and 9. And that could be, because what if I said find y of t between 10 and 12? It would be 0, wouldn't it? That'd be easy. Boy, ask me that on the final. You could then figure out when is this going to be non-zero and say, okay, in this case, I'm probably going to have some y of t between 4 and 5 because it's active between 3 and 9. But if we now flip and slide H, first thing we would probably do is flip it. So now we are at -2 and -4. And if we slide it, there's h of t minus lambda. And what could you do? You could actually say, well, he wants to know what's happening to y of t between 4 and 5. So now we could slide this up and find out what's happening between 4 and 5. Here's x. It was starting at 1, and then it was down to -3, and then it's 5. And at t equal to 4, do you see that this rightmost endpoint will be at 4 minus 2 or at 2? So we are asking what's happening when this guy is between this picture. How wide was I? 2. So this is t minus 2, and this is t minus 4. So we have this overlap. This is actually when t would be equal to 4, and when t is equal to 5, do you see that we would be looking at this picture. So now we want to know what's y of t when we move from red to green. Maybe I shouldn't be doing this. This is a completely different way than I've explained convolution before, huh? What was the question again? I don't blame you for asking. Essentially, how could you solve this question? You could do the whole bloody convolution and then just isolate on this interval between 4 and 5. And that would be one way to solve it. But what I've tried to indicate with the whatever I had, red and green, and those were not very good colors, I guess, to be showing this with. But if we did that, we're now saying, oh, here's where, and this is in the middle of one of our overlaps. So we would really be looking at finding this particular overlap pattern and finding y of t in that case. I think one of the questions was suppose we wanted to say what is y of 5? What is y of 5? Well, that's actually, this green is now the particular pattern we have when t is equal to 5. So this is now with t equal to 5. This is now equal to 3. And this endpoint is equal to 1. Do you see that? And now we don't even really have to do much integration. We just need to find area. We take whatever this value was it -1? So here is -1. And we multiply it by whatever the blue curve was at each point, which is 2. And it's how wide? It's 2 units wide. So really the area under the product of x with h of t minus lambda in this case is 2 times -1. It's -2 times its width, because we're completely overlapping that very first rectangular piece in x of t. So y of 5 would in fact be -1 times 2 times 2. There's too many 2's, but y of 5 would be -4. Y of t between 4 and 5 will be some function of t. And if you plugged in t equal to 5, you would calculate, hopefully, and get or obtain -4 for an answer. Do we want... Not sure I want to do too many more convolutions. They're time consuming, but we can... Here's one question that I think is very straightforward, but it's easy to obtain the wrong answer for. So let's just go through how you could avoid doing the wrong thing. Find the total complex power absorbed by the RL load when I sub g is 10 cosine of 20t, R is 5, and L is 2. What's the total complex power formula? What's something that you definitely need to know going into the final? I would say S is equal to V phasor, I phasor conjugate, where these are in RMS units. So S, the complex power, is VI star, where V and I are phasors, and they have their magnitudes written in terms of RMS units. If it wasn't in RMS, it would be V over 2, and it'd be 1/2 V max I max star. But I think it's easier to forget the 1/2 and just say, let's convert everything into RMS units. And here's where students will traditionally get hung up. What's I sub G in this case? I sub G is this current source, so we are given the current flowing through this R and L, the resistor and the inductor. But don't go too fast, because this formula now is assuming you have units that are in RMS. Is I sub G of t 10 cosine of 20t using RMS units? No, that 10 is an I max value, isn't it? So this is a maximum value for I. If we wanted I in RMS, it's now this 10 over the square root of 2. But we're only given a current. We aren't given a voltage. And that's our formula, VI star. Well, another way to approach this would say, well, if I'm given I's, maybe I should just focus on I's and say V is Z I, Ohm's law. And that works in max or RMS, right? So now if I used that in my S formula, now I just have to have the impedance and square the magnitude of my current. And I have the current. Actually, that's not really the phasor form. This is at 0 degrees, isn't it, if I use that as a phasor, since I don't have any shift in my argument of the cosine. It's at 0 degrees. Do I have Z? What's Z? Okay, it's now Z is equal to R plus J omega L. R was 5. Omega, 20. What was L? 2. So this is now 5 plus J, 40. And now we should be able to find it. Now S is 5 plus J, 40 times 10 over the square root of 2 squared. Or that's 5 plus J, 40, 100 over 2. Or that's 500 plus J 4000 over 2. Do we have a 250 plus J 2000 sitting in the answer somewhere? So that would be, and that's our volt amperes. That would be C. And the thing that tricks or makes students stumble is they immediately just take that 10 and use that for their I, not 10 over the square root of 2. So keep track of how your I is given to you. If it's given in terms of this time domain waveform I sub g of t, that's not in RMS units. I could give you capital I sub g and say, oh, that's 10 at an angle of 0 and the frequency is 20. Then you would get a different answer. And then I would have to tell you, oh, that's RMS, the I sub g. Since we're on this page, do you want to try this Bode plot problem or not? The straight line Bode plot sketch for h of s has a magnitude slope between 10 and 20 radians per second equal to some value and a high frequency phase equal to some number p1. That's actually the quickest one to look for. What's the high frequency phase in this transfer function? What's high frequency? Pardon? Yes, it would be a decade beyond that highest break, and that highest break is at 10,000. So you now say 10 times 10,000. It's at 100,000. That's high frequency in this case. And what is the phase at high frequency? How many zeros do we have? How many zero factors? We have 2. How many pole factors? 3. So at high frequencies, they're all going to be acting or already contributing their phase. So the 2 zeros phases will cancel 2 of the poles, and we have 1 pole active effectively at high frequency. And what's 1 pole produce in phase? Minus 90. So now you go, which of these have minus 90? So now I'm down to A and B. Is that clear how we got to that point? So now we've clued in on that. That's the phase at high frequency. Now the other one is a little more interesting. We say, what's the magnitude slope between 10 and 20? Now we have to plot the magnitude. We don't need to worry about its absolute value. So let's not worry about the constant. And let's just start looking at how this is behaving. We have a pole at the origin, so we're coming down. And then what happens? What's our next frequency that we break at? 0.01, and that's a 0. So now we're coming down, and at 0.0 we go flat. Don't we? And then what happens next? What break do we hit next? We now start going up at 1 because we have another 0 coming. So here is 0.01 and there's 1. And now what happens? Pardon? Well, that's supposed to be a straight line, but it's going up still until 100, and then we have effectively 2 poles active and 2 zeros active. We should be flat in terms of magnitude. And that was happening at 100. And then what happens? Then at 10,000, or 2 decades later, we go down. What in the world? I have no idea why it's... So what's the slope between 10 and 200 or 10 and 20? Well, between 1 and 100, we have this slope, and that includes 10 and 20. So we're going up at 20 dB per decade. Which is that, so it should be B. Do you see how we deduced that answer? We knew it had to be A or B, and now we found that between 10 and 100, we were going up at 20 dB per decade, just from a quick break perspective on our Bode plot. And voila, that gives us a plus 20 dB per decade slope. Because the only thing, well, what's active at that point is the pole at the origin and the two zeros. And effectively then they're going up at 20 dB per decade. Whew. Don't have a lot of time left. Do you want to see some power? I mean, not power or through the, but power problems. What do we have here that I could maybe, so you need to be able to do transfer functions. You need to be able to do three-phase and single-phase power. Suppose we do this one, or look at this one. A balanced YY three-phase system has a line current magnitude of 5 amps and a per-phase load impedance of 4 plus J4. Neglecting the line impedances, find the phase voltage magnitude at the generator source terminals and the total average load power. I would just start sketching what this tells you. One, you have a YY, and it says you have no impedance in the transmission line, which means that whatever we have at the load, that we can sort of say will have the same voltage on the load side as we have at the generator side. And what do we have here? We have a balanced three-phase, and it has a line current magnitude of 5 amps. So we have something really? Okay. I guess it thinks it's done, doesn't it? So we have a YY configuration. We know what the impedance is here, and we're asked what is the phase voltage here, and we know this impedance, and we were told that nothing is really happening there, but we were given this current. That was 5 amps. Do you see how you can maybe quickly find the voltage from capital A to capital N? You could just extract a single phase equivalent, and now you have something that looks like that's Ohm's law, isn't it? And this current, line magnitude current, was given in RMS units. And we're asked to find the magnitude of that, but do you see that VAN is now going to be 4 plus J4 times I sub AA. And we could just assume this is the reference phasor. We don't have to, but that just simplifies things. So it has an angle of 0. Or now we have 4 plus J4 times 5. Or that's 20 plus J20 volts RMS. And if we found the magnitude of that, wouldn't that just be 20 times the square root of 2, which is now one of our, or two of our choices. Now we have to find the power, but this would only be a power in one phase if we did something like Z times I squared. But that would be 4 plus J, well, in this case, it's just the real power. So now P in the phase is now R times I squared. So this is now 4 times 25, or that's 100, and that's in one phase. The total is 3 times that. The total now in the power, that's 300. That one's kind of, I think, an easier problem, but you can look at a little bit, well, are there questions on what we did there? You need to get comfortable with moving back and forth. You might have a Y delta, then you might need to convert the delta if it's balanced into a Y connection, and that's just a factor of 3 different. And you should be able to manipulate between line, which really means line to line voltage, and phase voltage. In this case, in the YY configuration, the line current is the phase current. But if it was delta, then you would have phase currents that would be different than your line current. Here, this phase voltage at the load is not your line-to-line voltage or your voltage between two transmission lines. That's not what you're asked in this problem, but you'll need to be clear on those relationships. Yes? So to find the V sub AN RMS, yes, all I did was I found the magnitude of this complex voltage. So now you need to keep track of everything as phasor quantities. Here and this is a voltage, but you're asked for your voltage in RMS. So now I just found the magnitude of 20 plus J20, and that's now 20 times the square root of 2. Because you have 20 in one direction, 20 up, you have an angle of 45 degrees. And that's this right triangle that has this hypotenuse factor of a square root of 2. So that's where that came from. And the fact that we didn't have any impedance in our transmission line, the voltage here from little a to little n is the same as capital A to capital N, that voltage drop. Other questions? I do have, wow, how many pages do I have? Goodness. I do have office hours if you have questions remaining, and we have about a week to prepare for this final exam. It's in the Chavez building. I have another review session coming up in a few minutes. Are there other questions? We will stop at that point. You can watch this at 3 times speed, and it won't take that very long.